Yeah, hello. Welcome back to the lecture 6. Talk is on energy storage technology. Professor Zunia, Professor? Yeah,
Sorry, I'm muted. Okay, so I think we can start.
yeah.
Let me share my screen. Okay, good afternoon, everyone. So this afternoon, the topic is energy storage technology. Because in the smart grid era, the energy storage systems are very important components, especially in accommodating renewable energy resources such as wind and solar power. Because these renewable energies are intermittent and their power output is not stable. So in order to cope with this intermittency, energy storage systems can play an important role. So first of all, I would like to give you a very general introduction to the energy storage technologies. Basically, they can be classified into 5 different categories, which are respectively mechanical storage system, electrical system, electrochemical system, also known as battery, okay, and a chemical system, as well as a thermal system. Okay? And for each of the 5 energy storage technologies, I will introduce some representative, specific, concrete technologies. For the mechanical energy storage, I will introduce the pump hydro, compressed air, and the flywheel. They are all very mature, okay, especially for the pump hydro. Compressed air, there are already some realistic projects. Flywheel is also commercialized already. Then for electrical energy storage, which are also known as supercapacitor, as well as a superconducting magnetic coil, I will also introduce the working principle. Well, for the battery, okay, battery is based on the electrochemical reaction to store the electric energy. So I will introduce the traditional batteries such as the lead acid, as well as the lithium battery. And another very promising and emerging battery technology is the flow battery. So we will introduce the redox flow battery as well. Now for the hydrogen, okay, the hydrogen, which is a kind of chemical energy storage, we convert we store the energy in the form of the hydrogen by electrolyzing process. And after that, we can use the fuel cell to generate electricity with the hydrogen. So this is also a type of chemical energy storage. Last but not least, the thermal energy storage. Remember, we have introduced the energy internet, right? One of the realization is to integrate multiple energy carriers, including the electric network, thermal network, cooling network, right? In my second lecture, I have introduced our research work on the multi-energy microgrid operation. So in this lecture, I will introduce a realistic district cooling system in Singapore. Okay, so that is based on the cooling energy storage. All right, so that is 5 different categories of the ESS. So when we evaluate or when we talk about ESS, we need to look at its system rating, as well as its discharging time at the rated power. So the rating is in the form of the megawatt or the gigawatt. Okay, it is quantifies how much power this energy storage system can charge and discharge. And on the other dimension, we also need to look at how durable this energy storage system is. For example, how long this ESS can charge and discharge. So you can see that for different types of energy storage technologies, if we start from the right side, the highest the highest rating, the energy storage with the highest rating is the pump hydro. Okay, the pump hydro. You can imagine that for the pump hydro station, the capacity could be very high. It usually at the 100 of megawatt or even gigawatt level. And after that, the compressed air energy storage, CAES, also has a very high capacity. Okay, very high capacity. They both have high rating and high duration time. So you can see they can discharge and charge for hours time long. Then after that, you can see in the middle, we have different batteries, flow batteries, lead-ion batteries, lead-acid batteries. Okay, these batteries has a different range of system rating from kilowatt level to 10 megawatt level, and they can charge and discharge for minutes duration time. So this battery, if you times the discharging time and the rating, you can estimate the total energy capacity. Okay. Now, so for the pump hydro and the CAES, they may usually for bulk power energy storage and management. And for the transmission and the distribution grid support, we usually use the batteries because they have relatively faster responding speed and they have a moderate system rating and system duration time. Okay. And you can see from the left side, we have high power flywheels and high power supercapacitors. Okay, this flywheel and the supercapacitor, they have a very fast responding speed than other storage technologies. So they are very suitable for power quality improvement and also used as the uninterruptible power supply, UPS. Okay, they can be installed at the data center or installed at a critical load site because their responding speed are very fast. So this diagram, I hope, can give you a general understanding of different energy storage technologies with different system sizing and their duration time. Okay. And now let me go through each representative energy storage technologies one by one. We start from the mechanical, the pump hydro storage. Okay, the pump hydro storage, by its name, you can imagine that the principle is to convert the to convert the electricity into the potential energy of the water. So specifically, we can pump the water from the lower reservoir to the higher reservoir. And in this process, we convert the electricity, we consume electricity, and we convert this electric energy into the potential energy of these water sources, okay, of these water sources. And once we want to discharge the power, we can directly turn on this generator, pump hydro generator, and let the water at the higher reservoir go through this turbine, and this pump hydro turbine will generate electricity, right? And in this way, we release the potential energy of the water sources into the electricity. So this is basically the operation principle, okay? And the advantages is as long as you have such reservoirs, the total investment cost over a long period, the whole lifetime, could be relatively low. And very importantly, such type of energy storage does not have a limited charging and discharging cycle, unlike the batteries. Okay, because for batteries, we sometimes can only use it for 1,000 or 2,000 cycles. But for the pump hydro, it has an unlimited lifetime. And the efficiency is also reasonably good. You can see the efficiency ranges from 70% to 85%. Okay, the power loss actually comes from the pump process, generator loss, as well as the water evaporation. Because for the water reservoirs, certainly the water is continuously evaporating, so that will constitute some power loss. Okay, so this pump hydro, as just mentioned, is the largest form of the energy storage for power grid. But it depends on the geographic locations. We can only rely on the existing, pump water reservoirs and the water sources to construct such hydro pump hydro storage. So sometimes, most of the time, they are located remotely from the load center. Okay, so this is something you have to understand. And even for the besides of the natural water reservoirs, we may also use underground reservoir. Okay, for example, the salt water and even smaller pump hydro station at the building environment site, because we can make a kind of water tank in the rooftop of the building, high-rise building, and then we can install such a pump generator turbine. And then we can do the same job to store the energy. That is also possible at the building environment context. Okay. And very importantly, you need to distinguish with the pump hydro storage and the hydroelectric dams. Okay, strictly speaking, they are different because the hydro generation plants, they can only produce power, right? They do not have the reverse function to store the energy. Okay, by pumping up the water. That is a difference between the two. So this one you have to be clear. And next is next mechanical energy storage technology is compressed air energy storage, CAES. And once again, by its name, I suppose you can understand the principle, right? When we want to store the energy, we just we just turn on the compressor and compress the air into the high pressure, high pressure form. Okay, so in this sense, the electric energy is converted into the potential energy of the air. Okay, of the air. But certainly the question is where to store this air. So we have to have a kind of underground cavern. Okay, very large scale underground cavern which can store this compressed air. And then when we want to release the energy, we can just pressurize. We can just let the pressurized air to go through the gas turbine, and this pressed air. When we hit this pressed air, it will release the very strong potential magnetic energy, magnetic force, and then can drive the combustion engine to produce electricity. So this is a basic working principle. Advantage is it has a very fast speed, because you can imagine how intensive of the pressed air is when it is released to drive the combustion engine. Okay, but once again, similar to the pump hydro energy storage, this CAES also depends on the geographic structure. Okay, we need to have underground cavern, which is not easy to find. And another disadvantage is this CAES, the efficiency is not good enough. You can see the efficiency is only from 50% to 75%. Why the efficiency is too low is because when we compress the air, okay, part of the energy becomes the waste heat. And after we release the energy from the pressurized air, it will also release certain heat, and this heat will be wasted. Okay, so this is a general structure of this CAES. You can see here we have the power grid, and here we have the underground cavern. Okay, this underground cavern certainly is kind of insulated from the external surfaces. So we have this motor, we have this compressor. When we want to store the energy, we just turn on the motor, it will drive the compressor, and the compressor will continuously work and compress the air in the underground cavern. Okay, and in this time, the air becomes highly pressurized. Okay, pressurized. And when we want to release the energy, when we want to generate the electricity, we just release the pressurized air. We can just heat this air. Then this air will immediately go through this combustion engine. Actually, it will go through this recuperator, high pressure turbine, low pressure turbine. This actually aims to use the waste heat, all right? Because when we depressurize the air, a lot of heat will be released. So this recuperator, high pressure aims to reduce this waste heat. And then this high speed and high temperature air will drive the turbine to generate the electricity. Okay, to generate the electricity. And during this process, we use the waste heat to improve the overall efficiency. Okay. However, despite the best efforts, the efficiency remains, 75% something. Okay. So this is one of the disadvantage of the CAES. Okay, the next one, the third one is the flywheel energy storage system. Okay, flywheel, once again, I suppose you can imagine its working principle. It must have a kind of wheel always rotating, and the principle is to convert the electric energy into the rotational energy in the wheel. Okay, in the rotation energy. So this is in this kind of flywheel energy storage. Basically, it also has a very fast responding speed, because you can imagine the very high speed of the flywheel, okay, And also its lifetime is quite long. It requires little maintenance because, for all the mechanical energy storage system, it does not require much maintenance. Okay. And because it's very fast responding speed, so this flywheel is very suitable for power quality application. For example, UPS and some electric vehicles are also using this technology. Okay, So you can see the efficiency is very high, above 85% to 90%. Okay, to 90%. Some power loss come from the kind of friction of this flywheel within the vacuum. Although it's vacuum, there is some vintage loss, so on and so forth. Now, this is the architecture of the flywheel ESS. Basically, we have this spinning rotor, the flywheel rotor, and we have this container. This container has to be a vacuum, so we also have a vacuum pump. Okay, we need to make sure this container is vacuum. Otherwise, the friction loss between the flywheel and the air can be significant. Okay. And the vacuum, and then we have the power grid, right? Power grid connected with this flywheel ESS, and we have a bidirectional generator, which can either operate as a generator or as a motor, And very importantly, you can see that we have the power inverter between the FES and the power grid. That is because when the FES produce electricity, its frequency may not be 50 hertz. Because you can see with the energy being released, the speed of the flywheel will decrease. So they cannot always maintain a 50 hertz frequency. Okay, so that's why we need to have the power converter. Okay, we convert AC to DC, then to AC again. Okay, when we want to charge the FES, we just use the electricity to drive the motor, and the motor will operate and reach a certain rotational speed of this flywheel. Then the mechanical energy stored in the flywheel will be the mechanical energy. And when we want to release, yes, we will just change it to the generator model. Then this flywheel will drive the turbine and produce electricity. But as I said, it may not be exactly 50 hertz, so it has to go through this AC, DC, AC converter before interfacing with the grid. Okay, so this is the working principle of the flywheel. Okay, this is some commercialized flywheel equipment. This one you can see has been applied in Canada. Actually, in our research lab, we also have a flywheel energy storage system in our lab that is about 100 kilowatt hour. Okay, so here you can see it again. We have a container, vacuum container. We have a flywheel, spinning flywheel, and then we have this generator and motor. Okay, so that is the working principle of the flywheel. Okay, then after the mechanical energy storage, the second one is electrochemical energy storage, and the common name is the batteries or rechargeable batteries. Okay, because even for the battery, some battery cannot be rechargeable, and this rechargeable batteries can be used as energy storage because we want to charge and discharge. So from the chemical perspective, there are mainly 3 types of the batteries, which are lead acid batteries, and this nickel, this nicid, lithium, they all belong to a kind of lithium type. Okay, and third one is called sodium sulfur, which is called Na type batteries. Okay, these 3 are very mature and already commercialized, but most major one is lead acid. Okay, lead acid. Now, basically, the principle is very straightforward. For this battery, you have 2 electrodes, and in the middle there are electrolytes, and there will be a chemical reaction taking place to convert the electrochemical energy in the electrolyte to electricity. Okay, so basically depends on the electrolytes, we have different battery technology. Now, lead acid is the most mature one. It's very mature. It's relatively cheap. Has a very relatively long lifespan. The responsibility is also reasonably fast, and it has a relatively low self-charge rate. So lead acid is very mature. However, the major disadvantage is its energy density, because lead acid is very heavy. So sometimes we only use it in our internal combustion vehicles. Okay, for electric vehicles, we have to use large-scale batteries. So we have to consider its weight and the value. So lithium batteries are mainly used in electric vehicles. Okay, and also for the power grid applications, lithium batteries has a better performance, especially under different harsh conditions, and it has also have a good energy density. So lithium battery nowadays is most popular. And the N-type battery, it has a high energy density, higher energy density, even smaller, lighter, and longer time span, and low maintenance. However, this N-type battery, compared with the lithium and lead acid, is not fully mature and widely commercialized. Okay. Yes, in our research lab, we have bought some small battery cell, and we have tested their performance. They really outperform lithium, but it's relatively more expensive. Okay, it's more expensive. Now, I think for the batteries, we have to consider its specific technical specifics. So basically, we need to look at, apart from the rating and also the lifetime, we need to look at the energy density. Okay, so basically the energy density can be the energy to weight or energy to volume. Okay, and also we need to look at their lifetime and their economic. Give me 1 second. I need to. Sorry. Yes. Okay. So basically, for these batteries, we need to analyze these different specifics. So for the lead acid, okay, lead acid is very mature and viable old technology. So it has a disadvantage I already mentioned, a low energy density, so these lead acid batteries are mainly used for stationary application. For example, backup power supply, and sometimes for the power grid, microgrid application. They may also be used as UPS, okay, uninterruptible power supply. So look at these specifics. In terms of the energy density, you can see 33 to 40 watt-hour per kilogram, 60 to 100 watt-hour per liter, and the power 118 watt per kilowatt. And discharging efficiency, this is very important, because during the charging and discharging, certain power will be lost, depending on the chemical reaction, depending on the, condition and status of the battery. So basically, the lead acid battery may have accurate efficiency ranging from 50 to 95%, okay, depending on the technology. and the materials. Okay, and the energy, the price. Okay, the price is certainly also an important concern. So this number probably is not updated, but it just to give you a sense. You can see the lead acid battery are relatively cheap. Okay, self-discharge rate. Even we don't use the battery, the chemical reaction will also naturally happen, and it will lose the certain energy stored inside. So this will be quantified as a self-discharge rate. So for lead acid, this self-discharge rate is around 3 to 20% per month. Okay, if we take at 20% per month, that means if you do not use the battery, after 5 months, it will be discharged fully. Okay, so try to recall that if you have a car, you don't use the car for a certain time, let's say for 1 or 2 months, you cannot turn it on because the battery is, fully discharged naturally. And the cycle durability, that is the lifetime. Okay, during the charging and discharging, the chemical reactions, they will lead to some certain, accumulations of chemicals, and this will increase the internal resistance of the battery, and correspondingly, the capacity of the battery will decrease. Okay, so when the battery's capacity is below 80%, we consider the battery is dead because its performance cannot be guaranteed. So we need to use a kind of cycle lifetime or cycle durability to know how many cycles will make this battery dead. So for lead acid, you can see it's not that good, only around 350 cycles for most of the case. And the cell voltage, okay, the cell voltage is the standard voltage for each individual battery cell. It's for lead acid, it's about 2.1 volts. And another important parameter is operational temperature range. Okay, you can see this lead acid can operate between minus 35 degrees Celsius to 45 Celsius degree, which is quite wide. For some lithium batteries, its performance will degrade significantly at the low temperature environment. So for electrical vehicles, they may not be suitable to be used at the very low temperature area. Okay, so that's why we also need to consider this temperature range. So this table shows some specific concerns, specific parameters when we evaluate the battery technology. The next one, apart from lead acid, the nickel cadmium. Okay, the nickel cadmium is also a kind of major battery technology. Okay, it has also been used for standalone power UPS, electrical vehicles, power grid. Compared with the lead acid, this nickel cadmium battery has a higher energy density, higher power density, longer life cycle, and better performance, especially at the low temperature environment. Okay. The major concern is the toxic nature of this cadmium, because we need to, after this battery is retired, we need to dispose it. So we have to consider carefully these toxic materials for recycling. Okay, so this is for the nickel cadmium battery. So look at its parameters. You can see that energy density much higher compared with the lead acid, right? And the power capacity also higher. Discharge efficiency similar, and self-discharge rate much lower, only 10%, and the cycle lifetime is much longer, 2,000 cycles. So this one really has, better working performance, but we need to consider is toxic materials inside. Okay, the next lithium battery, I suppose everybody is familiar, because nowadays our cell phones, our laptop, and even our electrical vehicles, they are all using lithium batteries, because this is the most mature and the most viable technology. And we have abundant lithium materials in our world. Okay. So basically, the performance of lithium batteries is most balanced, okay, in terms of the self-discharging rate, in terms of the energy density, in terms of every dimension, it has a very balanced performance. However, the safety of the lithium battery could be a concern, especially during some extreme events, let's say for electrical vehicle, when it experiences a car accident, the whole battery may explode. right? Because the materials in the lithium of the material, they contain flammable electrolyte. Okay, so that is a concern. The safety is sometimes a big concern. Now, if you compare its technical parameters, you can see, wow, energy density very high, okay, very high energy density, very good efficiency. The price is continuously declining, so nowadays everybody can afford it. And the self-discharge rate also very low, only 2%, and the cycle durability also high, more than 1,000. Okay, more than 1,000 cycles. So lead-acid battery is very popular nowadays. But even under the lithium battery type, there are specific different materials that can do this battery. So basically, we have this LFP, we have NMC, we have different materials for the electrolyte and also for the electronode. Okay, so lithium battery is certainly a very research-intensive topic in material science, engineering, electrical engineering. Well, many people are working on that. In terms of the company, many big companies, the CATL and the Samsung, Sony, they are all doing these lithium batteries. Okay, so that is the status for lithium batteries. Okay, the next one I would like to introduce is the flow battery. Okay, flow battery by its name, it is the electrolyte. I mean, the energy is installed in the flow format. Okay, in the flow format. Specifically, these chemicals are known as VR, vanadium redox, and this polysulfur, brodo, zinc, bromine, and okay, anyway, they are just a kind of flow liquid type materials that can store the electricity. Okay, and among them, the VR, the vanadium redox, is successfully commercialized. Okay, even in our university, my colleague has a kind of startup to do this redox energy storage, and it has already been applied in Singapore for many applications. Okay, so clearly for different materials, they have a different technical performances, and certainly they have different techno-economic properties. But let me introduce the working principle. Okay, the working principle, basically you have two tanks. Negative and positive, and in the middle there is a kind of membrane, the ion exchange membrane. Then for the negative electrode, positive electrode, you have connected them to the liquid material. And once you want to charge the power, okay, the chemical reaction will happen, and the electrons will flow from one side to another side. Then it will generate the electricity, right? And when you want to store the energy, you just connect the power source to this electronode, and it will drive the electrons move in a reverse way, and so the energy can be stored. So a very important feature of this flow battery is that the capacity of the battery, the battery depends on the volume of the liquid. So if you want to increase the capacity, you just put more liquid into the tank. So compared with compared with other battery cells, this flow battery is more flexible, right? It's more flexible, and you can see that this is some commercial products. This is a big tank. You just put this different chemical liquid into it. Then depends on the volume of the liquid, you have different size. That is the so-called flow battery. Okay, flow battery. Now, once again, let's summarize the working principle. Energy is stored in liquid electrolyte, which flows through a reaction chamber. Okay, reaction chamber. In the redox flow battery, two chemical components are dissolved in liquids and separated in a membrane, just I illustrated. And the ion exchange will happen through the membrane and then generate the electric current. Okay, so energy available is related to the electrolyte volume. Okay, so that is makes the whole system more flexible than the battery cell. But if you look at the technical performances, okay, the biggest advantage of flow battery is its lifetime. Okay, you can see it has 100,000 cycles lifetime. but its energy density is not good, certainly because it stores the electricity energy into the liquid form. So the energy density, power density is not that good, but the time duration, time durability, cycle durability, they are very high. And the efficiency is also not bad, 75 to 80%. So that is about the flow battery. And the chemical storage, the third type, okay, the third type. The third type is chemical storage, which means we directly store the electric energy into a chemical form. And one of the highest energy density type of the material is hydrogen. Okay, hydrogen we have introduced in the previous lectures because it is fully clean, right? H2 is fully clean. It does not produce carbon. It does not produce emissions, pollutions. The question is, how can we generate hydrogen from the electricity? Now, this can be done through a so-called electrolysis process. Okay, electrolysis process. There is a kind of electrolyzer equipment, and you put the hydrogen and you connect it to the electricity. It will generate hydrogen and the other O2, oxygen. Okay, oxygen. So that is how you can generate hydrogen for charging purposes. And if you want to discharge the power, the hydrogen can convert it back to electricity by fuel cells. A fuel cell is another kind of equipment. It can directly produce electricity using hydrogen. Okay. The biggest advantage of hydrogen is a very high energy density by weight, but relatively by volume. Yes, you know, hydrogen essentially is a kind of a gas. So we have to compress it into the liquid form. So that part we also need to consume certain energy. So in order to store the hydrogen, we need to have the so-called compressor and the specific container. And besides, the hydrogen can also be converted directly to mechanical power in vehicle through the combustion engine, because essentially when we burn this hydrogen, it can immediately release heat, right? So this one, hydrogen can also be used as a fuel, okay, to generate electricity or drive the vehicles without converting back to electricity. That is also possible. That's why nowadays there are also hydrogen type vehicles, just as I show here. So here you can see in Japan, Toyota is very advanced in hydrogen vehicles. They just use the hydrogen as a fuel instead of the gasolines. Okay, and besides, there is fuel cell type bus in USA. This hydrogen is used by the fuel cell to generate electricity, and the electricity will drive the electric motor to produce electricity. So that is another way. Now, this figure shows the working principle of the hydrogen and the fuel cell. So basically, as I said, the fuel cell is to convert the hydrogen into electricity. You can see the input. There is a chamber, right? Chemical chamber. You have anode, you have cathode. So hydrogen go to the anode, oxygen from the air go to the cathode. Then chemical reactions will happen in this exchange, proton exchange membrane. Then this chemical reaction will move the electrons from anode to the cathode so as to generate electricity. And in the meantime, this chemical reaction will also produce heat. You can see that a certain heat will also be produced. So if we're able to make use of this heat, we can improve the total energy efficiencies, right? This one is especially useful in the multi-energy system, Okay, so to summarize, a fuel cell converts the stored chemical energy directly into electrical energy. That's why there is no intermediate process. Then in this case, hydrogen is passed over anode and oxygen passed from cathode, as I just showed. Then electrons will flow from one side to another side. Okay, so various types of fuel cell are invented, including the solid oxide fuel cell and the permeable membrane fuel cell. Okay, depends on the chemical materials. So that is for the chemical storage represented by fuel cell. Okay. Then the next one, the fourth one is electrical storage, which by its name is directly store the electric energy into the kind of device. But before that, let's have, it's already 40 minutes. Let's have a 5 minutes break. Let's have a 5 minutes break before we move on. Okay. 5 minutes break. Please come back at 4 after 5 minutes. Okay, welcome back. So let's proceed to the first type, the electric storage. So by its name, the principle is to directly store the electrons. So in practice, this electrostatic device is also called supercapacitors or ultra capacitors. I suppose everybody knows a standard capacitor, right? Basically, you have two plates. Then in the middle, there is insulation, dielectric insulator. So once this two plate is connected with a power source, the electrons will be attached to these two plates. Okay, so this is the general principle for standard capacitor. However, the capacity of a standard capacitor is very low. It's in the millivolts or even volts level. So it is not for the high power application. In order to store large scale electrons, large scale electric energy, we need to have this supercapacitor. Okay, supercapacitor. So this supercapacitor may have special materials. For the dielectric insulator, it may also have multiple layers and different series and parallel connections, so that it can store large scale electric energy. But the working principle remains the same. It consists of two parallel plates that are separated by a dielectric insulator, as you can see. This plate will hold opposite charges when induce an electric field where the energy is stored. Okay. Now, since there is no other intermediate process, for example, mechanical energy storage and electrochemical energy storage, the responding speed of this supercapacitor is extremely high, right? Because it does not need to convert to other formats. So it is very useful, very suitable for high power application. And besides, since there is no intermediate conversion process, it has an extremely long lifetime, around 1 million cycles. In other ways, it's almost infinite. It's almost infinite lifelong. So it's useful for the high power application, for example, power quality application. The question is, the energy density of this supercapacitor is relatively low. If we look at the energy, right? Energy is the, integral of the power over the time. So because the nature of this supercapacitor, we may not be able to have a very, very large size of the device, but its power density is very high. Okay, power density, right, can immediately produce high power. Okay, so in practice, we sometimes will combine the supercapacitor with other energy storage technologies as a hybrid system. Okay, for example, we can combine supercapacitor and the lithium-ion battery together and make use of the advantages respectively. For supercapacitor, you can see its charging time is very low, which means its responding speed is high compared with the lithium-ion batteries. Right? Life cycle, the supercapacitor is almost infinite. Cell voltage doesn't matter because essentially they are connected into the modulars and connected to converters. And the energy density, you can see energy density. Yes, supercapacitor is not good because we cannot have a large size. But the lithium-ion battery, they can have a high energy density. But the power density, okay, power watt over kilogram, supercapacitor outperform much better. Okay, it's 10,000, but lithium-ion is just 1,000. Okay, the cost is another issue. The cost of the supercapacitor is today remains very high because essentially we need to have a specific devices materials compared with the lithium-ion. This supercapacitor is more expensive. But importantly, this supercapacitor, it can work over a wide temperature range, okay, because essentially it is a direct format of the energy storage. Okay, so it does not matter for extremely low or high temperature. But the lithium batteries is different because it is based on a chemical reaction, so the temperature will have an impact on its performance. Okay, so that is about the electrical storage. So sometimes, as I said, we can combining the two as a hybrid system and make use of their respective advantage. Okay, so this is a so-called hybrid battery, ESS, and with supercapacitor. Another type of electrical storage is the magnetic superconducting coil. I suppose you have heard of this superconducting, right? Superconducting means the resistance of this material or this system is close to zero. If there is no resistance, you can imagine that the energy can always be stored in that material, in that kind of coil. So that you can see here, the energy stored in the magnetic field created by the flow of direct current in the coil, right? However, the key challenge is how do we achieve superconducting? Okay. Nowadays, in order to achieve superconducting, we need to lower down the temperature to kind of 0K, to an extremely low level, 0K or 7.2K. So this is a low temperature superconductor. And if we can increase a bit, the temperature for realization 10K to 150K, this is called high temperature superconductors. Okay, so under this extremely low temperature, these materials, conductors, the coils, they will have close to zero resistance. So you can imagine that this superconducting magnetic device, they have a very high power capacity and instantaneous discharge rate, right? Especially similar to supercapacitor, the electrons are directly stored in this device. So there is no intermediate conversion stage. Now this is a structure, illustration of a structure of the superconducting magnetic energy storage. Basically, you have a container, and once again, this container has to be vacuum, and it has to operate under a extremely low temperature, right? 0K or to 100K. Now you need to have this coolant. You need to have this coolant to make the low temperature. However, when you generate this cooling, it will also consume electricity. So the total efficiency of the entire system will be a concern. And inside, this is a coil. Okay, this is a superconducting coil. And once the temperature is below a certain range, it will have almost zero resistance. So that is about the superconductor type of energy storage. Okay, the last one I would like to introduce is the thermal electric energy storage system. Because at the in the first day when we introduced energy internet, right? One realization of energy internet is to integrate multiple energy networks. For example, electric networks and the thermal networks or cooling networks. So when we generate the cooling or heating from the electricity, and once we cannot consume this thermal or cooling energy, we need to store them. We need to store them properly and use it later. So this thermal energy storage is a device that can, store the cooling or heating for a relatively long time, because it will have insulated containers. And note that sometimes this thermal energy cannot convert it back to the electricity. This one you have to understand, because according to the physical laws, right, the heat cannot be converted back to electricity. The wasted heat. So, for example, the solar energy falling on the heat pipe may be converted to heat and then stored in the water tank. Okay, so the heat energy is stored in the form of the hot water, and then it will be used for heating applications, warming, or for other air conditioning, so on and so forth. Another present application is the storage of the chilled water. Okay, the chilled water is for the cooling purposes, of course. So this one is especially useful in Singapore context because our average temperature is always high, 25 to 30 degrees. And a near future application is the thermal storage using molten salt. Okay, a different material, because the waters compared with the molten salt, the insulation and the energy storage property of water is not good as good as this molten salt. Okay, so I see many of my colleagues are doing this type of energy storage. This molten salt is called the phase change material. Okay, when the heat, the thermal energy passes through this material, the phase of this material change, and it will store the energy in one format. And later on, you can be used for either cooling or heating purposes. Now, this is an illustration of the thermal energy storage system. Now, basically, you can see this thermal energy storage can store both cooling energy and the heating energy. Okay, so basically, you have this is our consumer. Okay, this is our consumer, and this is the so-called aquifer. Okay, aquifer. Then basically, there is a heat pump and also a heat exchanger. Now, the principle is that the cooling energy stored in this container, and it will go through this pipeline and exchange the heat with the load, okay, with the consumer through this heat exchanger. And after that, this remaining cooling energy will go through this heat pump. Then it will restore, go back to the original device. And this device will be continuously chilled, okay, for cooling energy. So this is for the summer application. And for the winter application, it is a reverse. We do not need the cooling anymore. So we just pump the heat water, okay, through this pump and exchange the temperature, the heat with the heat consumer. And after that, the wasted, hot water will go back to the device. Okay, go back to the device, and later on it will be reheated. So that is the so-called working principle of the thermal energy storage. So very importantly here, you can see there is no power-related device. That's why I just said the system may not involve conversion from or to electricity. It's just store the heat and the cooling energy. So very important device here is exchanger. Okay, exchanger will determine the efficiency of the system, and also the heat pump. It will decide the speed and also the efficiency of the whole system, as well as the loss. And of course, this aquifer will decide the efficiency, the energy loss of the whole system. Okay, so we need to have proper materials to insulate the container from external temperature. So that is the thermal energy storage. Let me show you some realistic examples in our country. In Singapore, we have this district cooling system. Okay, a company called Keppel is doing this district heating and cooling system, supplying the cooling and heating energy to the customers. So you can see here we have a thermal storage tank. Okay, thermal storage tank. Then there are two pipes. Of course, one is for one is going through, one is going back. And this is a district cooling plant. This one is to generate heat or cooling. Then on one hand, the generated thermal energy will go to the consumers, okay, to exchange the temperature, exchange the temperature with the consumers' buildings. And after that, the wasted chilled water or hot water will return back to the chiller cooling plant. So if the thermal energy is not fully consumed, it will be stored in this thermal storage tank. And here, the thermal storage tank is based on the hot salt. Okay, it's not the kind of hot water, because the insulation of the water is not good as molten salt. So you can see here the thermal energy storage tank is based on this molten salt. Okay, then this molten salt, they can store the energy more efficiently. So this is a so-called phase change materials type thermal energy storage. And this one, we have in Singapore, we have the world's biggest underground district cooling network. So you can see we have this chiller plant. This chiller plant is to produce chilled air and chilled water for the cooling purposes for the entire region. Okay, for entire region in CBD. Here I will show you. So this is the CBD of Singapore. So we have such a chiller plant located here, and we have pumps connecting to different commercial buildings. This is a shopping mall. This is the biggest hotel, and this is a museum and many other commercial buildings. So this chiller plant can directly supply the cooling energy. Okay, so that these buildings, these customers, they do not need to install air conditioning anymore. Okay, and in such a centralized form of cooling energy generation, we can have a higher energy generation efficiency, right? Because we have the kind of scale effect. Okay, you can imagine the whole region is covered by this centralized chiller plant. So they do not need to have the individual air conditioners. So the total energy utilization efficiency can be much higher. So that is about realistic district cooling network located in Singapore. All right, so after that, I think I have covered all the 5 different types of the energy storage technologies. And for each type of them, I have introduced some representative technologies. I only cover the major working principle because the detailed control system, detailed chemical reactions are too detailed. So we don't have time, and there is no necessity to study them in such a course. Okay, so I just give you a general understanding of this ESS technology. Now let's make a summary of them. Because in the next lecture tomorrow, I will introduce the applications of the ESS to power grid. So for different applications, we need to have different technical specific parameters. So that means we need to select different energy storage technologies. For peak shaving, we probably need large scale ESS, right? For UPS, we just use a small scale but faster responding batteries. Okay, and for the power system frequency control support or some other market dispatch support, we may also need to have a cost-effective energy storage systems, which have a longer lifetime. So that's why we need to go through all the ESS technologies and understand their different properties, different technical performances, and different, suitabilities. Okay. Now let's make a summary. So the large grid energy storage are known as pump hydro and compressed air, because the size, the scale of this system could be very huge. So economically, it's very viable as long as we have these water reservoirs, we have these underground caverns. So as long as you construct such a energy storage station, economically at the large scale, it is quite commercially viable. Okay. However, these pump hydro and compressed air are not commonly seen because they fully depends on the geographic locations. Okay. And besides, most of them are located in a remote place from the load center. So in order to connect them to the power grid, you also need to construct the transmission grid. So that is also something you need to consider. And the flywheel, another mechanical energy storage, is used for niche application, which requires high power, long lifetime, and faster response. But the biggest concern for flywheel is the price. Today, it remains very expensive. In our lab, we have one kind of system which is not cheap. So flywheel, but ideally flywheel is a very good type of ESS because it has a long lifetime, very fast responding speeds, and less requirement for maintenance. Okay. And the electrochemical batteries, okay, they are difficult to be scaled up because of the cost and the limited charge-discharge cycles. For the batteries, basically, the batteries are in the form of the battery cell. Okay, each cell has a very small capacity and a standard voltage. So if you want to have a large-scale energy storage system, you need to connect the cells into modules, into packs, and these packs then can be connected into the systems. So there are different configurations, different connections of the battery cell pack module connection. And then this whole system need to connect with the power converters before connecting to the power grid. So they are quite complex technically. So sometimes it's not easily to scaled up because of these concerns. And besides the batteries, especially for the lithium batteries and other batteries, the materials, they are either toxic or they are flammable. So we have to consider the safety issues and also the disposal, the environmental issues when they are retired. And very importantly, the batteries, they have a limited lifetime. As I just shown in these tables, lithium batteries, they may have around 1,000 life cycles, but some others may have less. For example, lead acid only have several hundreds life cycle time. So that is for the batteries. Specifically, once again, lead acid and nickel cadmium have been used successfully for small microgrid applications, and lithium have issues of high cost and safety. But nowadays, with the advancement of the technology, the lithium batteries cost has been continuously declining, and its safety can more or less be guaranteed. Okay, especially for these big manufacturers such as CATL, Samsung, Panasonic. They are very advanced in lithium battery manufacture. Okay, the flow batteries and the sodium sulfur have been experimented on, but yet to achieve market acceptance. That is also this has also been changed, especially for the flow batteries. As I said, the redox battery has already been commercialized. So our university has a startup producing this redox flow battery, and they have already been installed in some microgrid system. Okay, so I think I'm fully confident that these flow batteries will become more and more mature and become more and more viable technically and commercially. Okay, so that is flow batteries. And the chemical batteries, known as the hydrogen electrolyzer and the fuel cell. You have to distinguish that this hydrogen, okay, electrolyzer is to make hydrogen, But in order to generate electricity, you need to have the fuel cell. So in other words, the hydrogen-based energy storage should contain two systems. One is electrolyzer, one is fuel cell. But unfortunately, both of them today are still very expensive. So you can see that they are not fully commercially viable yet because they require substantial infrastructure investment. Okay, this is something we have to consider. But I suppose in the future, because the hydrogen is so advantageous in terms of the energy density, as well as its cleanness, and many industry companies and government agencies, they are very supportive in developing this hydrogen. You know, in Australia, the government has set a hydrogen plan. They want to make so-called green hydrogen from the wind and solar power, so they can make use of this hydrogen for different purposes. And very importantly, the hydrogen, in addition to generate electricity, they can also be used as a chemical materials to make other products. So the hydrogen is very, very promising in the near future. Then electrostatic supercapacitors, of course, they are very expensive. They are used only to hybridize a cheaper energy storage device to achieve higher power capacity. That is what I have mentioned. We want to have a hybrid energy storage system which can leverage advantages of different systems. So supercapacitor has a very, very high power density, but energy density is bad. So we can combine it with lithium-ion batteries, lead-acid batteries, or other energy storage technology, so that as a combination, they can provide many more advantages than individual devices. And the magnetic and thermal energy storage technology are still very experimental, especially for the magnetic. You can see the superconductor, well, it's almost impossible to realize in the near future. Okay. And the thermal energy storage, as I just shown here, actually they are already commercialized, especially this molten salt. They are already commercialized, and even in Singapore, they have already been practically deployed. So that is something we need to know. Okay, and another very important thing about the energy storage system is to understand the different characteristics. Because next lecture, we will introduce the different applications. So we need to have a good understanding of the technical specifics. So clearly, different energy storage technologies, they suit different applications. Some applications require high percentage of certain factors such as safety, cost, power density, and energy density. So here I list a table from a review article about the technical specific parameters of different ESS technology. You can see for the lithium and for this flywheel, for this SMES, supermagnetic, and this SCES supercapacitor, right? Flywheel. You can compare the density, power density. You can see supercapacitor always have a highest power density. And then in terms of the cost, okay, in terms of the cost, lithium is also expensive, and the energy density, right? In terms of the with respect to kilogram weight, with respect to volume, and the energy cost, okay, the energy cost, and the cycle efficiency, okay, cycle efficiency very important, and life cycles, okay, life cycles. So you need to have a clear understanding of the different properties for these different energy storage technologies. Then after that, we can select the most suitable technology for a practical application, which will be the next lecture. Okay, so next tomorrow morning, I will introduce several specific applications of the energy storage technology. Okay, so that is the end of the slides. Then let's have a Q&A. Let's have a Q&A. Any questions, please? We still have around 10 minutes to answer your questions. Can I skip PPT? Yes, yes. Later on, we'll share the PPT with Professor Kumar. Yeah. Any questions regarding the energy storage? Response time of the flywheel, yes, it's very fast. As we introduced here, flywheel certainly, because the speed of this spinning wheel is high, so it has a relatively high response speed. Okay, so response speed is not an issue. Okay, for flywheel, yeah. Any other questions? Okay. Any questions? I understand it's a Sunday time, so everybody is tired. I appreciate your attendance on this Sunday afternoon. How to design supercapacitor for simulation? Okay, you can use MATLAB Simulink. There is some models for supercapacitor. And yeah, you can also use Simulink to simulate the batteries, okay, lithium-ion batteries. Okay, there are a lot of toolbox.
Professor, the flywheel energy storage system will be supporting for a shorter duration of the time depend. Is it so?
Sorry, can you repeat your question?
No, the flywheel energy storage system will support for a very shorter duration of a time.
Yeah, yeah. The energy capacity is not that high because depends on the size of this system. So in our research lab, the size is 100 kilowatt hour, not that big. Yeah, 100 kilowatt hour. Flywheel, I'm not sure. You can check. You can check whether there is a flywheel in the Simulink. But I suppose yes. I suppose yes. Yeah. And I know there is a new module in MATLAB called Sim. Let's see, SimsGo, SimsGap, SimsGap simulation. Let me see. I know there is. You can use the battery modeling package to do this. You can see here. I can show here. There is a battery pack modeling in Simulink. Yeah, SimsGape. Yeah, SimsGape actually is a very advanced toolbox. So I have attended the tutorial here. The SimsGape, you can see it can measure different type of the batteries. It can model different cells, packs, even the cooling plates, battery energy management system. So you use this SimsGape. Yes, very useful. Okay, you ask about for 80% of renewable penetration, what amount of energy storage capacity is required? Okay, this one depends. This really depends on the system. Depends on whether this system is able to host so much renewable energy. Okay, so there is not a kind of deterministic value. But you know, in many countries, the agencies or power grid utilities, they have set a standard. In China, okay, as far as I know, for wind and solar power, you have to at least deploy 20% capacity of the energy storage. Yeah, so in other words, if you have 1 gigawatt wind and solar power, you have to have a 200 megawatt energy storage deployed. That is a standard requirement in China. For other countries, I'm not very sure. But the optimal size of the energy storage really depends on the system, including the system network topology, the voltage level, the load characteristic, as well as the renewable power output characteristic. Yeah, whether the power output is the intermittency, right? Depending on the intermittency. If the wind power is quite steady, so probably the energy storage is not needed much. Especially in UK, right? In the North Sea, the wind power are quite steady, so energy storage may not be needed much. But for other countries, for example, in Singapore, our solar power, we have very variable weather conditions, so the solar power output is fluctuating very fast. So we do need batteries, energy storage. Can we design a lithium above 10 megawatt? Yes, yes, for grid application. Yes, you know, in South Australia, Tesla has already deployed 100 megawatt lithium battery for power grid support. Yeah, so nowadays you can easily find lithium battery system beyond 100 megawatt. That is not an issue. Yeah. Okay, any more questions? Energy storage prone to cyber attack in any way? Essentially, yes. If the energy storage system is connected to the system SCADA system, or connected, communicated with the control center, certainly cyber attack may happen. Yeah. So cyber attack does not depends on the equipment. It depends more on the communication network, right? So yeah, it's certainly possible. But the most important concern for the energy storage, especially lithium battery, is their safety. You know, if you search online, there are a lot of battery energy storage station fire accidents in Australia, in many places. So I think this is also an important concern. SMES, you mean the super magnetic? No, this is still very, very expensive. Yeah, super magnetic, superconductor magnetic energy storage. No, as far as I know, they are not commercialized yet. For the last few minutes, could you share a few words that demonstrate any simulation? Last minute of which part do you mean? You mean which part of the sharing? You mean the summary, right? The summary. Yeah, the summary. Okay, I can probably. Next lecture, I will show how this energy storage system is applied in power grid for frequency application and peak shaving. So next day, tomorrow, I will show the examples and the simulation results. For the simulation results for frequency, we are also using the Simulink. So wait a second, if I can quickly show the lecture slides for tomorrow, you can see here we have this simulation model. We have this LFC model in Simulink. Then we can deploy this Simulink model and simulate the frequency. And this is the frequency results. Yeah. So tomorrow I will talk more on that. Yeah. Lisa, when the losses is more during charging, that really depends. You know, the power loss. If you are talking about the power loss also internal loss depends on the internal resistance of the battery, and the internal resistance sometimes depends on the temperature. So that also depends on the temperature of the internal battery, depends on the SOC, state of the charge, and the charging rate, right? And also depends on the depth of discharge. So it's a very complex problem. It's not a linear. Sometimes it could be higher during charging. Sometimes it could be lower during the charging. That really depends on the charging rate, SOC, and what else? The depth of discharge. But if you are talking about the capacity loss, okay, capacity loss is because during the charging discharging, during the chemical reactions, it may accumulate some materials in the electrolyte. Then this will degrade the available capacity in the battery. So this one also depends on the depth of discharge, okay, which means how deep the battery is used, charged or discharged. So yeah, that really depends. Okay, any more questions? Then I think after half an hour, right? Half an hour, Professor Kumar will teach you the simulation on power converters. Okay, for another 2 hours.
I'll take a break for 5 minutes. Start.
Okay.
Okay, thank you, Professor.
Okay. Thank you, guys. I will see you tomorrow. Tomorrow morning, we'll talk about the energy storage system applications in smart grid from 8:30 to 10 a.m. And tomorrow afternoon, I will introduce the distributed generation. Okay, distributed generation for from 1 p.m. India time.
Yeah, Babu, you have raised your hand.
Yes, sir. Sir, excuse me. Could you please tell the efficiency of the energy storage system, maximum efficiency? Is it the cycle? Is the cycle? Yes, sir.
Yes, the efficiency of different technologies are a bit different. Okay, the highest efficiency certainly is the electrical energy storage because there is no conversion process, right? So you can see the super capacitor. Yeah, for other type of technology, you can see the efficiency are different. But least ion battery efficiency is quite satisfactory, 90% something. Yeah, because during the charging and discharge, certain power is lost, right? Certain power is lost, energy is lost.
So the maximum, the battery, lithium-ion battery is the maximum efficiency, sir.
To my knowledge, some products claim to have 95 or 97%. Okay. You can take 95 nowadays. 95 is a conservative number. Lithium battery.
Okay, sir.
Hmm.
Thank you.
Okay, thank you, guys.
Thank you,
Let's
Professor.
finish here. Hope you have a good rest, then continue with the next session.
Yeah.
Okay, bye bye.
What we do was, can you join back after 5 minutes? I'll just close the meeting for this lecture. Again, there should not be any recording issues also. All of you, please join back again, maybe within 2 minutes.